and I'm going to be today I'm going to be answering the essential question: if during the Cuban Missile Crisis they had used a bomb to destroy America, how long would it take? Excuse me. How long would it take for the radiation levels to disappear entirely? And my guiding questions for that are: how much radiation is released in a nuclear bomb? How is radiation measured? Can radiation last forever, or will it last forever? When does radiation wear down, and at what speed? What kind of radiation is released in a nuclear bomb? What kind of bomb was aimed at the U.S. during the Cuban Missile Crisis? What kind of radiation is in a ballistic nuclear missile? What does half-life mean? How do you convert half-life to full life? What is the half-life of uranium-235, and how much uranium-235 is in a ballistic nuclear missile? Alright, real quick before we start this, I would just like to put a big disclaimer about how in my essential question I asked how long would it take for the radiation levels to disappear entirely. Now, when I wrote this, I did not know that basically radiation, it doesn't sort of disappear at one point. It just sort of gets smaller and smaller until we can't really describe how small it is. So this question isn't really feasible, I suppose. So I think we're just, for the sake of this, we're just going to modify it a little bit, and we're going to stay and said how long would it take for the radiation levels to get so low that we couldn't describe how small it is with a unit of measurement. And so yeah, let's so first off, I think we should start with a little bit of background history about the Cuban Missile Crisis. Basically, it was a time near the end of the Cold War in 1962 when Cuba had aimed a bomb at America for around a month. And now the type of bomb that was aimed at America was called a ballistic nuclear missile. Now that is a type of that is like a type of missile. The one bomb name in particular that we used was called an Ivy Maker. And I got this information from the info on the Ivy. I mean, not it. Apologize. It's not Ivy Maker. It's the Ivy King, and I got that from the Wikipedia page of Ivy King, paragraph 4. And so basically, we're going to be using the amount of so basically how the missile works is that there's an amount of an element called uranium-235 that it has like inside of it, and then when the bomb detonates, the uranium-235 goes under a fission process. So basically what we need to do to figure that out is how much uranium-235 was in the Ivy Maker, and that is about 60 kilograms. Oh, and I also have a picture to show the Ivy Maker. I mean uranium-235, and it is right here. So basically, what we like I said, there's about 60 kilograms of uranium-235 inside the Ivy Maker. Now, I also get that information about from the Wikipedia page on Ivy King, paragraph 4, and so basically, getting right into this, we need to getting right into the math part of this, we need to take the 60 kilograms of uranium-235, and what we have to do right now is that we have to multiply that number by 1.3%. And the reason we have to do that is because that when I said it underwent a fission process, it means that the atoms in the uranium-235 atoms sort of split apart. Now, the thing about it was that only about 1.3% of the uranium-235 sort of undergoes that fission process. So basically, that means that we get about 59.22 kilograms of uranium-235 that don't go under the fission process. So basically, what we have to do with that number, like I said, we're trying to, like I said at the beginning, we're trying to get it to as small of a number as possible. So basically, one way we can do that is that we can convert it into an even smaller number, so we can get an even more exact result. So, basically, since the kilogram is in the gram unit, I decided to just stick to that unit of measurement. Unit of mass. So, the smallest unit of measurement in the gram system is called the yoctogram. Now, a yoctogram... Wait, hold on. I forgot. Let me get a picture to show it. Alright, so there we go. So, basically, so that's the yoctogram right there. Alright, so basically, to tell you about how small it is in comparison, a yoctogram let me just rephrase that entirely. So a kilogram is equal to about 10 to the 27th power yoctograms. I'm not really sure how I can phrase this. I apologize, but yeah. So about 1 kilogram is worth 10 to the 27th yoctograms. There we go. So yeah, that's basically how small it is. So in order to convert it easily, we just need to take the amount of uranium-235 in kilograms, 59.22, and then multiply that number by 10 to the 27th, which equals, hold on, this is a very big number, as you would assume, about, let's see here, 5922 followed by 25 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Boom! That is our number. So yeah, as you would, it's a pretty big number. Alright. Yeah, moving on. So what we do after that is that since we have the amount it would take, now here's where the half-life of uranium-235 comes in. So, the half-life of uranium-235 is 700 million years. Now, just a quick sort of disclaimer, I guess so, is that, when they say half-life, it's sort of not, it's not like, since the half-life of uranium-235 is 700 million years, it wouldn't mean that we just double it to get the entire lifetime of uranium-235. That's not how it works. How it works is, say we had 60 kilograms, I guess, still. And then, so 60 kilograms, and then after 700 million years, 30 kilograms would be left. And then after 700 million years, 15 kilograms would be left. So you get that point. So, basically, going back to this, all we need to do is times this number by the amount, we just have to times this number by 700 million to get our answer. So, I guess we should get right into it. So, we just need to do 59.22 to the 27th power, and then multiply that number by 700 million years. And that equals out to be, let me see right here, where is it? Aha! About 413, 54, followed by Let's see here. 32 zeros. 1, 2, 3, 4. Wait, 33 zeros? Sure, 33 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Excuse me real quick while I double check something. Alright, that's it. That's the entire number. Now, if you really wanted to know about this, excuse me real quick while I add these commas. If you wanted to know how it'd be like in like word format, I'm sorry, it would go like, it would be 441 duodecillion 354 tridecillion. That's wow. I'm even impressed. I still get really surprised about that whenever I say that myself. So if you really wanted to know, if you wanted to put that in like comparison for other things, the star, like the sun, will probably have an entire lifetime of about 10 billion years. So that would be like that. That is a total of 10 zeros altogether. And 11 digits. Like, that does not even compare to this. And the Earth has only been around for what? 4.3 billion years? Yeah. It's kind of a mind. Like I said, I still honestly cannot manage to handle the fact of how big of a number this is. So there you go. And if you want to hear my citations again, thank you for listening.